Okay, so continuing on what we talked about with graphs, we could have a graph like this. We could have a graph that has points A, B, C, D, E, F. And connected, I think we kind of drew one like this last class. The points are all connected like that. Then if the edges had values, so this is a graph where the edges have values or weights. 1, 2, 2, 3, 1, and let's say 3 here. Okay, so we could ask questions about the graph like, what's the shortest path to get from, say, A to F? That's one possible question. So every time you take an edge, you get charged this much money, let's say. Okay, so what would be the shortest path from A to F?
Between B and E, yeah. Between B and E, what is the
Okay, so...
distance?
What is the charge between
Oh,
B and
right,
E?
right. You mean, okay, yeah, let me get that marker. Let's say this is also 1. That's right, you couldn't answer the question. So, okay. So to get from A to F, what's the...
A, B, E, F.
A, B, so 5?
Yeah.
And there's no, this would be 4.
9, that's coming up to 9.
Yeah. Okay. A, B, E, F would end up being the shortest path. Okay. Now let's ask a different question. So what ends up happening in a lot of the computer science classes you'll take, where there's graphs involved, you're given a graph as input, and we talked about last class how we could represent this as input. We could do it with a matrix, like an A, B, C, D, E, F by A, B, C, D, F, and put a 1 if they're connected, a 0 if they're not connected. And then if the edges had weights, instead of putting 1 meaning connected, we would put a number, like 3, meaning they're connected and the value is 3. And then we said last class that if there's no connection, we would put a number like infinity. Right? Because if we put 0, it means they're connected and the distance is 0, and that could get confusing. So we want to put a number so large that you would never take that path. Okay, so now suppose we had a question. Last class we said that a graph that has no cycles, so this actually has 3 cycles. This cycle, and then 1 outer cycle. So this graph actually has 3 cycles. If we wanted to create a graph that has no cycles, from these points, so this would end up being a graph that is taken from here, but we're going to throw away a few edges so that there's no cycles, right? So, I mean, I could throw away this edge and maybe this edge, and then we have no cycles, right? So I could do this, right? I could just say, like, here's an example of a no-cycle version of that graph. It's still connected, every point is connected to each other, but now there's no cycles, because I chose to get rid of this edge, and I chose to get rid of this edge. But what if, so you can see we could do, there's many versions, there's many trees that we could make from this graph by throwing away edges just to eliminate cycles. What if we wanted to make the tree that covers the whole graph, to make it a connected graph, but there's many different versions, many different trees that will keep it connected, but there's might be one that is the smallest one. So what would be, like, so I'm keeping the graph simple enough that we could see it. What would be the corresponding tree that connects all the points together, there's no cycles, and out of all the possible ways we could do it, it's the one with the lowest edge count? And actually, as you're coming up with the answer, the answer to this question is pretty intuitive. We'll see some questions that are not intuitive. But how would you go about finding the tree? So it's a tree that covers all the edges, so they say it spans all the edges, and it's the one that has the minimum cost. So they end up calling this the minimum cost spanning tree, or MST, minimum spanning tree of the graph. How would you figure out how to get the graph?
Is it DABEFC?
So we would keep this edge. Would we
AB.
keep this edge?
Yeah.
This one?
Yeah. BE,
This one we'd keep.
EF,
EF.
and C.
And which one to C?
FC.
FC?
Yeah,
This one?
yeah.
So we got rid of this cycle by getting rid of this edge.
Right,
And we got rid of this cycle by getting rid of this edge.
right.
But we actually kept this one. So the total cost of this tree is 1
2.
plus 2 plus 1 plus 2 plus 3. So that's 1, 3, 4, 5, 6, 7, 8, 9. So the minimum spanning tree is 9. But is there an edge that's kind of big in this one that we can get rid of? But if we get rid of it, then obviously there's going to be some point hanging out there by itself. We have to somehow bring that back in with a cheaper edge, with a less expensive edge.
How about getting rid of DE and EF, sir?
Okay. Keep losing the eraser. Okay. If we get rid of this edge,
DE and EF.
and this one,
Yes. We connect BC and CF.
okay. Well, if we connect this one, now this point is out by itself. Now the only thing left is we have to make sure this point's connected to the graph somehow.
Okay.
We have two choices. We could either add this one or this one.
Oh, the minimum will be EF.
EF. So this ends up being, the cost of this one ends up being 2, put a 1 here, okay. 3, 4, 5, 6, 7. 7?
6, sir. Okay, 7.
Yeah, 7 altogether. So the minimum spanning tree, the size of it is 7, assuming we have the right minimum spanning tree. And it makes sense that some graphs have more than one minimum spanning tree. Obviously, there's tons of spanning trees. Like we could just, anytime we end a cycle, we have a spanning tree. The minimum one is the one that has the lowest total cost, and there might be some ties. So like for example, if this was a 3, then we had a choice. How do we include F? Well, we could have taken this one or this one, and we went looking for the smallest one. If it's a tie, then either one would work. So we could have several minimum spanning trees. So yeah, this ends up being called a minimum spanning tree. So now we can think of this graph. This is a spanning tree that came from this graph. If we wanted to, we can just spin the pieces around and say the graph looks like this. All I'm doing is drawing the same exact graph, but I'm drawing it looking more like a tree. Because even though this is a tree, by definition there's no cycle, so it's a tree. We're kind of used to seeing it like this.
B and
Yeah, B and
F.
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 And then
B is connected to
B
A and
has
C.
2 children, has an A
And C.
and a C,
And A also.
and A has a child D. Okay, so this is exactly the same graph as that. It's just this stretched around, right? No difference. And then, if we wanted to map this graph back to this one, we have an edge. I'll draw these as dotted edges from D to E. And there's
D
an
to
edge
E is done.
from C to F. There's an edge here. So the ones in blue are from the minimum spanning tree, and then the other ones are just to complete the graph. So this is actually, this graph and this graph are really the same graph. So if we take a graph, create a spanning tree from it, and then we draw dotted lines to include the edges we've missed. We can sometimes refer to this edge here is referred to as a back edge. That's an edge that takes you back to an ancestor that's, you know, like a child going back to their parent or grandparent or so on. That's considered a back edge. It's from the point of view of the spanning tree. And an edge that goes from like a cousin to an aunt, that's what they sometimes call a cross edge. Okay. But anyway, we could take basically any graph and convert it into a tree. When we're converting it into a tree, we're basically looking at all the cycles and removing an edge. If you're looking for the minimum spanning tree, then every cycle you hit, you want to remove the most expensive edge. Okay, so if we have a graph, so now we'll just focus on graphs that have graphs that are trees. So suppose we had a graph like this one. Now in the past we've had examples where at the nodes there are values. So suppose we had values like I should have made the letters show up in alphabetical order. Okay, well they're not in alphabetical order, that's fine. Suppose we wanted, the nodes have these letters, A, B, A through F. And suppose we decided we want to search this graph for a particular value. Let's say we want to search this graph. Does this graph have a C in it? So I think if we said last class, they refer to a graph like this as a tree, a graph without the green edges. It's referred to as a tree because it has no cycles. But we kind of said last class, it's kind of like a bush, like a tree kind of goes tall for a while and then goes wide. This thing goes wide right away, and that's kind of like a bush, right? So it's really a bush, and it's upside down. So we were saying last class, we call it a tree, but it's really like an upside down bush. So we start at the root, and then it starts going down, and it gets wide right away. If you were to search for each node saying, is this a C? No. Okay, I have to search somewhere else. Is this a C? Is this a C? Like, what order would it make sense? What order makes sense for you to, the nodes to, what order would you search these nodes in? Obviously, when we're going to represent this graph in a computer program, we're going to have the points that are connected together, and we're going to have one node identified as the root, where we start from. That's typically called a root, where the tree goes into the ground is the roots. So we have a root node, and we're going to start there. And if that's not the one we're looking for, we're searching for C. So we're searching for, and then let's say we're searching for the node C. Does our tree contain a C or not? This could be like your friends' names or something, and you're looking to see if you have the phone number listed, so you go looking for a match, and if you see the friend, they're there. If not, your cell phone has your friend's name, or they don't. And if they don't, you have to add it. Okay, so we're searching for C. Starting at E, we say, is that C? No, it's not. What would you do next? Just like kind of off the top of your head, would you?
Either go to the left child or the right child.
So, okay, would you check? Okay, so you go to the left child, that's not it. So here's the order you're checking. You're doing this one first. Let's say this one's second. Now, it's not that one. Which would you go to next? There's really no right answer, but...
The left again, A.
So you would go to this one. Okay. So this would be the third one you would check.
And then fourth will be D.
Right, so as your pattern seems to be going, keep going as left as you can. Then if you run out of stuff to look for...
Then come to C.
Okay, but somehow we have to be able to keep track of where we are. So we got here, and we said, there's no more children to look at, we're here. The only information we really have, because we're gonna represent this in computer memory, we know who we're related to, so we could go back to A, and this has no, because this could have had more children. We go back to here and realize there's no more children to look at. Then let's go back to here. Now this one has more children, so now you would go to this one. So to get from D to C, so that's the pattern you want, but you have to actually work your way backwards to here. So now we check C, and now we found it. So this would end up being the fifth one you check. If this wasn't here, you'd have to go back to the parent, say, are there any more children? Nope, no more children. Okay, let's go back to the grandparent. Yes, there's more children, you'd come here and search there, right? So that's one pattern. So one pattern is kind of like, starting at the root, go as left as you can until you can't go no more. Then go back one level and say, is there anything this way? If there is, you go down here and then start going left again until you can't go no more. Just keep doing that, like, keep going left until you can't go anymore, hop back up, go left, hop back up, go left. Eventually you'll cover the whole tree. So that's one way to do it. And that pattern is called, you're going deep into the tree, like right away. Because you were suggesting, like, do the children, then do all the grandchildren, then do the great-grandchildren, and that's another way. But this way, this one, because it goes deep pretty quickly, is referred to as a depth first search. You're going like deep right away. So you're going deep, then you're working your way back slowly. You slowly work your way back up to the top, then go deep again, and so on. Another way to do this, another way to search, would be...
You could start from the base as well. Left node, and then the root node and the right node.
Right, so you would, again, you're always searching from the root, because you'll have an identifier where the root is, so that one you kind of get for free. So you'll search this one first, and then you look at all the children first. So search this one, that's not what we're looking for. Now search this one, I'll search this one third, that's not what we're looking for. Now go to all the grandchildren, and we'll do this one fourth, do this one fifth, and now we found what we're looking for. There's really no right or wrong answer. If the answer is somewhere over here, your method is better. And if the answer is like the second child but over to the right, then your answer is better, but it's kind of random, so there's really no right or wrong answer. But this type of searching is called breadth first search. Now, if we were to implement this on a computer, and the implementation would be something like this. Let's say we chose this adjacency matrix. We said we can represent this picture in computer memory by doing this, creating a 2x2 matrix. A, B, C, D, E, F. A, B, C, D, E, F. B is connected to E, so B, E, so one there. E is connected to F, E is connected to F, there's a 1 there. We put a 1 wherever there's a connection, a 0 wherever there's not a connection. When we visit a child, when we're at E, and we want to say, are there any children, we would have to go to the E row, which has B and F. It would have a B and an F. We'd have to go through this, so that it would look like this. We'd have to go, after we're done looking at E, we'd have to say, do you have any children? A is not a child, B is a child, so let's go visit B. Now, after we're done visiting B, your method, the depth first search, doesn't want to see that it has a child F. It says, we'll get to that one later. At this point, you now go to its child, A. A has D as a child. So A has D as a child. So as soon as we're done looking at E, we jump up to this row and say, do you have any children? And it has D as a child. Then we jump to D. D has no children. Well, D is connected to A, but we don't want to keep searching the same thing over and over. We'd have to somehow mark A as being searched already. So when D says when we go looking through D's children and it has 1, it's already been searched, so we kind of consider that we're
Yeah.
done searching D. So when we write our computer program to solve this, you'll do this in another course, you would be doing something like that. But you have to keep track of children you've already visited, which ones have you visited, which ones have you not visited. And if we used your method, after we're done with E, we would look at its children, which is B and F. We would look at B and say that's not a match, and then we'd look for more children right away.
Yeah.
And then we do F. So really just, we could write the program to do it, but it just determines which one do we check next. But those are two very common ones. I don't even know if there is a better, other than those two, if there are any way. You want to make sure you hit every vertex,
Yeah.
and
How about bottom-up approach, sir? Is there,
we'd have to know, because the way we'd represent this, we'd have like a root is E, we record that. So basically we would record the graph and then we also record the starting one. If there was some way we could know the bottom ones, like D is the bottom one, so check that first.
like, left node, go to its root, and then go to the right from that root? But the second approach seems to be more simpler compared to others. Like the breadth first appears to be simpler than other methods.
They both end up being mechanically about the same, and the amount of time it takes to search the tree ends up being approximately the same. But it might be a little easier for the mind to follow because you're going level by level by level.
Yeah.
But you can see either one is going to eventually hit every node, and it won't take longer. It really just changes the order you're looking at. Actually, the breadth first one ends up being used more often than the depth first search one ends up being used more often, because like if you remember last class we talked about a search tree where the stuff we're looking for is like everything less than E is here and everything greater than E is here, so we can kind of look at this value and then just say, oh, that whole half of the tree is pointless now. So we could start doing combinations of that. We'd have a tree that's not a perfect search tree, but it's somewhat of a search tree, and we could start to rule out sides of trees, and in that case then the breadth first search one might be better. Because then we could say, well, I know this child and all the ancestors are not worth searching. We could kind of dismiss chunks of the tree, whereas if you're going level by level, you have no choice but to search the whole tree. But that would come later on. Okay, so another type of graph problem. So what we've now done is we're drawing graphs, which is basically vertices and edges. We could put numbers on the vertices, so those are values that are typically we're searching for something. We could put numbers on the edges, so then we're trying to maybe figure out what's a minimum way to get from one point to another. So suppose we had a graph like this. This is an interesting problem. I think someone proposed this in 1950, in the 1950s or so, but let's say we had a graph like this. A, B, D, C, yeah, like a diamond shape, like this. And also, last class we said we could have directed graphs or undirected graphs. So just to recap, if there's an edge between A and B, this means you can travel from A to B, or you can travel from B to A. But if we put an arrow on it, it's like a one-way street. You can only go from A to B, not B to A. And we can represent that in computer memory too, like this. We could have A, B, C, D, A, B, C, D, and we're thinking of it like this way. This node can get to that node. So we can get from A to B, but we can't get from B to A. So B to A is a 0. But A to B is a 1. Okay. And let's say we have this, and we have this, and we have this. Okay. And let's make it a what we call a weighted graph, meaning the edges have values on them. And not just, right now if there's no edge, you can kind of think of it as a 1 and a 0.
Yeah.
But if it's got a number, then it's a number instead of a 1 or a 0. Now what we can do, instead of having numbers, we could have functions on the edges. So we could say, this one is a 2, this one is a 2, this one is 1 plus, let's say x over 100. It's a function now. So what's going on in this graph? Let's say you need to drive from point A to point B. And let's say this is a highway that has a lot of lanes, like 6 lanes long. So no matter how much traffic is on the highway, you can still go the same speed. It's not like you're going to slow down because of traffic. And it takes you 2 hours to get from A to C. Then, when you, and to go from point B to point D takes 2 hours. Doesn't matter if you're the only car or if there's tons of cars, it will always take you 2 hours. These roads, this road and this road, there's only 2 lanes. And if there's a lot of traffic, you're going to slow down. So, it could take you, if you're the only car on the road, it will take you 1 hour. X is how many cars are on the road. But if there's more cars, it might take you an hour and a half, right? Like if there's 50 cars on the road, it's going to take you an hour and a half. If there's 100 cars on the road, it's going to take you 2 hours, right? So like that, okay. Now suppose there's a total of 50 cars. No, I'm sorry, 100 cars. And let's say, just to, for argument's sake, this is going on all day. Every hour another 100 cars show up, or maybe when you get to the end, you go back to the beginning and start over, right? So like it's kind of this, these 100 cars are in this system all the time. What would be the smartest way for the 100 cars to go? Like 75 should go one way and 25 should go another way. What would end up being the smartest way for them to go? So it's a symmetrical graph. It always takes you, the only 2 ways you can go are this way. You can either go this way, or you can go this way. Right? It's going to take you 1 plus 2, 3 hours plus whatever this comes out to be, to get there.
You have to get from A to D, it doesn't matter.
Yeah, A to D is what we're trying to do.
Yeah, but if you have to get to A, from A to D, we have to either take A, B and B, D, or A, C and C, D.
Right. Those are your only 2 choices. And let's say you have like GPS in the car, so you can see, oh, there's a lot of traffic going here, so I'm going to go this way. Like you can, you're trying to do what's best for you. So how should these 100 cars split up? So it's going to definitely take, whichever path you take, whether it's these 2 or these ones, it's going to take 3 hours plus something. And the something is based on traffic. So if all the cars went this way, it would take 100 cars, it would take all cars 4 hours.
4 hours.
And this whole road would be empty. So that would take 4 hours. So if they all went across the top, 100 go A, B, D, following that path. If all 100 did that, it would take 4 hours. Everybody would take 4 hours to get to their destination. Is there a better answer?
50 and 50.
Okay. Yeah, so, and basically because it's symmetrical, probably the 50-50 split makes sense. So if we have 50 go A, B, D.
1.5 plus 2 is 3.5.
And 50 went from A, C, D. Then how long would each take? It would take, to go from A, B, D, it would be 1 plus a half plus 2, 3.5.
On just one way.
Each car would take 3.5 hours.
Yeah.
And going this way would also be 3.5. Okay, so this would end up being 3.5 hours. Okay, and is there any way, now if you were entering the system and you knew it was 3.5 each way, is there any way you could make it better? Could they ever do anything better than 3.5? So in this particular case, it's kind of intuitive. A 50-50 split is the best thing to do. So half the traffic goes this way, half the traffic goes this way, and you're getting this as small as it can be. If 51 went this way and 49 went this way, then the people who took 51 would be taking 3 hours and, 51% of an hour. And the other one, this would be a better way. And then people would hear on the news, hey, there's less traffic here, and then they'd start going this way. So eventually it'll hit what they call an equilibrium, where it's now even, right? And that would be the best answer. So suppose, so this is like a very interesting graph problem, because we're not assigning a number to the edge, we're actually assigning a function to an edge. And there's a real world example, a real world application for this. This is the way traffic goes. The more cars, the slower you go. So sometimes you have to put a function on an edge. Now, what if an edge was added, a new edge was added from B to C? Right, so the police come in and they open up a new road that goes from B to C. And this road only takes 1/4 of an hour, 15 minutes, to get there. Can we use this road to make things better?
We could either from A, B and B, D will be one way. AB to BD will be one way.
Okay, so there's how many ways can we get from A to D? We could go
3 ways here.
three ways. A, B, D, A, C, D, and then A to B,
A, C, B, D.
CD.
Okay,
A,
it's
B,
B, C,
C, D.
okay.
So now there's a third way. So this could only help,
Yeah.
right? Could this make things worse? Intuition says it can't make things worse, right? Why would adding a new road make things worse? Okay, now, suppose people did, and so now there's one thing we're adding to this question. People are gonna do what's best for them, okay? So, right now as it stands, it's 3 hours, it's 3.5 hours to go this way, 3.5 hours to go this way. Now you show up, and you have the traffic report. You can see in your GPS, 3.5 hours this way, 3.5 hours this way. Can you think of a way to get there faster with this new road added? Right now, this
3.25 A, B, C, D,
A, B,
C, D.
C, D will now take, as it stands, an hour and a half plus 1/4 of an hour plus an hour and a half.
3.25.
3.25.
Yeah.
Okay, so now at first you're the only person who knows about this. So you're the only one who knows about this new road. So you can go 3.25. 3.25. Everyone else is going 3.5. But actually, you've now added yourself to this road and to this road. That's part of your path. So you're starting to add to the traffic. So even though you're helping yourself, you're making more traffic. Now other people start thinking of doing that. So people are now saying, well, here's my choices. 3.5, 3.5, 3.25. I'll also take 3.25. So that other people start doing it, right? And eventually it's going to hit a new equilibrium. So at one point, all 3 of these paths will take the same time, and everyone says, well, now they're all equal. So who cares which one you take?
So that 3.25 A, B, C, D, we get 3.25 only when we consider half of the cars there. So we'll have to find another path for the remaining 50 cars. Like we got 3.25 considering
That you're the only one who knows about this path, and you're the only one taking it,
okay.
okay, but you see it, so you take it. And you're the only, but now everyone else starts to see it, right? So they now have a choice. I could do, so this actually, since you took this path, it's really like, if there's 100 cars in the system and you come in as the 101st one, it actually went to 3 hours and 51 100ths, a little bit more. These two times went up a little bit because you now took this path, because you're causing more traffic. Slight amount of more traffic. But, so anybody entering the system has these three choices. Well, this still looks like the best choice, so then a few more people start taking it. At what point does it no longer have an advantage? So like the last time, the equilibrium happened when 50% of the cars went this way and 50 went this way. Now, when will people choose to not take this new, better path? At what numbers? Let's say it was, like, just take a guess at it. What do you think it would be? Like, 40 cars go the old way, 40 cars go this way, and 20 take the new path?
Yeah.
Right, let's try that. If 40 cars went this way, and 20 cars went this way, that would mean 60 go across here and 60 go across here, right? So if it was 40 doing this, 40 doing this, and 20 doing this, how long would each path take? The old path would be 3 hours and 60 divided by 100, 3.6 hours.
1.4 plus
3.6, this would be 3.6. And how long would the new path take? That would be 2 hours, 0.6 plus 0.6 is 1.2, 3.2, 3.45. So what's happening is all these new people who are taking the zigzag path are making this road have more traffic on it than the original system. So we're still not at the equilibrium yet. So even if we got to this point where 40 cars were going this way, 40 cars were going this way, and 20 were going like that, this path still is the best one. So some more would go. Eventually we would hit the point, I think the equilibrium for this question ends up being 25, 50, 25. 25, 25, and 50. I think that's the case. How long? So we want to see, how do we balance it so that they all the times come out the same? And at that point, then it doesn't matter what path you take. If that was the case, this would take
1.25 plus 2.
1.25.
3.3 quarter.
Yeah, because 25 cars are going this way,
So 25
And-
by 100.
and 50 cars are going this way, this way, this way. So 75 cars are going along here,
Okay.
right? 75 out of 100,
3 by 4.
so this would be 3.75. 3.75 hours. 25 cars. So yeah, also 25 cars are going this way, and 50 cars are going this way. So 75 cars go along here. So that would be,
The same.
yeah, so this path is 3 hours and 75. And now this path, the cars that go this way are going 1.75 plus
1.75.
1.75 is 3.5, plus a quarter is 3.25.
3.2.
Right, so they're all 3.75, right?
Yeah.
Which sounds crazy, right? When this road was not here, everybody used their head and took 3.5 hours. Now we had a new road, which makes things better. Everybody got all greedy, and now they're all slowing down. So this is yeah, some famous paradox thing with graphs. But I just wanted to point out, once you start putting functions where one value changes as other values change, you have to be aware, don't use intuition. It doesn't make sense. Here, you think this extra road is going to make things better. Well, maybe it's no one will use it and it stays the old way, but it actually makes things worse. Okay, and then another kind of interesting, this is just one of those, like an intuitive question. If we had a graph that was graph, this is one without edge values or node values. But if we had a graph like this, try to keep these simple, but if we had, so this is kind of a question you might be able to answer based on like intuitive properties of a graph. But we said last class one of the walks I think was a Euclidean walk where you start at one vertex and you travel along an edge to another one. Can you walk around these points in such a way that you cross every edge exactly one time? So like for example, this graph you can do it. Can we take this graph and starting at one point, can we cross every edge exactly once? Yeah, we could just start here, we go this way, this way, this way, this way. We crossed every edge exactly once. Can we do that with this graph? So you start doing like a little trial and error. Well, let me start here, and I'll go here, and then I'll go, you know, here, and then back, and then over to this guy. But now I need to cover this edge, and one of these.
Yeah.
So that's not going to work. You start trying a few, and you might eventually. So did anyone see an answer, or can you see that there is no answer?
Mm.
Like if we started, we can start here.
Two.
It starts to look symmetric, so this way and this way is really the same thing. So we go here
To A.
to A, obviously along one of these edges, you have to record which one. If we come back to here, we could then go up to here, take one of these two into here. Now we have two more paths to cross, but if we take either one, we can't get to the other one, so that one ends up not working. But what we might want to start looking for are like properties of the graph. If you had a graph, if you had a point in a graph with an edge going out of it, so let's say here's a graph and we decided to pull one point out of the graph and focus on it. If we could start here, and if we started here and took one edge into the remainder of the graph, and we were able to hit every edge, we have to at the end come back here. That makes sense, because we went from this point into the graph. If we ever come back here, we have no other way to get back to the graph. If this point has exactly two edges connected to the graph. If it has four edges, if we started here, we'd have to go into the graph, at some point come back to this point, go back into the graph, and at some point come back. So really, if an edge has even number of, if a vertex has an even number of edges, if you start there, you have to finish there. We couldn't start here and finish somewhere else, because then we would have left out one of our edges. If we didn't start here, let's say we started within the graph, we have to cover this edge, so we'd have to go out here, come back, go out and come back. If we don't start here, then we can't finish there. We'd have to finish somewhere else. So just like kind of high level thinking about graphs. What if a vertex had an odd number of edges connecting to the remainder of the graph? Okay.
We don't end at that point. Even if we start here, we don't end at that place.
If we start here, we cannot end here. Because we go into the graph, we have to come back and then go into it, and then we can never come back. So if we start here, we can't end here. And if we didn't start here,
we could end
you actually have to, right?
there.
If we don't start here, if we started somewhere in here, we would travel to here, come back, and then travel here, and we can't go anymore. So if we either have to start here or have to end here.
Right.
There's no, right, otherwise there's no solution. What if a graph had 3 points that were odd? 1, 2, 3, 1, 2, 3, and 1, 2, 3. Well, if we start here, we have to end somewhere else. And if we started here, we have to end somewhere else. So wait, if we start here, we must end here, but then this point's a problem, right? So a graph can have at most 2 points that have odd numbers of edges. If there's more than that, there's no way this can be done. And this graph has, this is 3, this is 3, this is 3, and this is 5. So if one of these points, if you picked one as the start point, the other 3 have to be the end point, and that can't happen.
Even number of vertices can have odd number of paths. Should have odd number of paths. If odd number of vertices have odd number of paths, then there is a problem.
Yeah, so actually you start thinking about some properties like the total number of, if you added up how many edges come into a point, since every edge on an undirected graph goes from one point to another, it would all have to add up to be an even number, right? So 3 plus 3 plus 3 plus 5, it has to add up to an even number. If it adds up to an odd number, there's something you're missing. There's an edge that doesn't hit a point, or something's wrong there. So it's just like a question like this is just getting us thinking about properties of graphs. That the graph, if every point had an even number on it, every single point, then every point has the property that if you started there, you have to finish there. And if you didn't start there, then you cannot finish there. And therefore a graph, there's a theorem that says a graph like that, where every point has an even number of edges incident on it, there is definitely at least one path that covers every edge. And you could think about it like just, if 4 edges, or any even number of edges, were going back to the graph and coming through, you're going to the graph and coming back, and that would be true for every point. So that would be an example of a graph that does have that property. And if the graph, if every point was even except for 2 that were odd, that would also have a path. You would start at one of the odds and you'd have to finish at the other odd, and you'd still be able to cover every edge. But once there's more than 2 points that are odd, and it actually has to be an even number of points that are odd. You couldn't have 3 that are odd, because eventually they all add up to an even number. So it's either 2 or 4 or 6 or 8 that are odd. But as soon as you get more than 2 odds, then there's no way to have that path. But if it's 2 or less, then you definitely have that path.